Welcome to section 6.1, Law of Sines. We're going to be looking at how to solve triangles that are no longer right triangles. So obviously up until this point our whole focus was on right triangles. Now we're able to solve things that are not right triangles. So one of the ways that we're going to do this is use what's called the law of sines, and we'll talk about what that means. So we're going to learn to use the law of sines to solve what's called oblique, which are non-right triangles. And then we're going to look at two types today. AAS and ASA, and I'll talk about what those mean. Maybe you remember from geometry as well. So first, just as a quick review, let's just kind of go through back how to solve right triangles. So to solve right triangles, you have an example where B is equal to 3 and angle B is 25 degrees. So remember, when you have a right triangle, your angles typically A, B, and C, but no matter what you label them, the side across from the angle is always opposite that, in the sense of if angle B is 25 degrees, then the side opposite angle B is side B, and this is equal to 3. And so the side opposite angle C is side C, and then the side opposite angle A is side A. So when you solve a right triangle, you find all the values that are missing. So we have three values that are missing: angle A, side A, and side C. So to find angle A, because it's a right triangle, we know that they have to add up to 180, or specifically the two acute angles have to add up to 90. So to find angle A, it is equal to 90 minus 25 degrees. So 90 degrees minus 25 degrees, and that is equal to 65 degrees. So we know angle A is 65 degrees. And when you do the angles, you round them to the nearest tenth when we need to, and then the sides round to the nearest hundredth. So now that we have both angles, we can now use our trig functions to find the other sides. Now, we want to really make sure that we are using the information given to us in terms of B equals 3 and angle B is 25 degrees. When we start to use the information that we have found, if we made a mistake, then obviously we're also going to make a mistake on any time we use that. So for side A, if I stick with B equals 3 and 25 degrees for angle B, what trig function is that? That would be opposite over adjacent, which would be tangent. So we would do tangent of 25 degrees is equal to opposite 3 over adjacent A. And then we solve. We multiply both sides by A. So that's A times tangent of 25 degrees is equal to 3. Divide by tangent of 25 degrees. Now when you plug this into your calculator, make sure your calculator is in degrees, because our angle is degrees. And since it's a side length, we are going to round to the nearest hundredth, and we should get A is equal to 6.43. Alright, and then we'll do the same thing with side C. Side C, though, is hypotenuse, so we have opposite and hypotenuse. So opposite and hypotenuse is not tangent anymore. Opposite and hypotenuse is sine. So we will now use sine of 25 degrees is opposite, which is 3, over hypotenuse is C. And then once again, multiply by C, divide by sine of 25, and you'll get a side length, once again rounded to the nearest hundredth, of 7.10, and include that 0 in there because it's not exactly 7.1. We rounded it to 7.10. So we have three things. We have C equals 7.10, A is equal to 6.43, and then the angle A is equal to 65 degrees. And so that's how we solve right triangles. You find all the different values, the angles and side lengths that are missing from that. So example 2 just goes into another kind of example for right triangles. I'm going to solve it, but I'm going to pause the video and do it. I want you to find angle A and side C. And so you can now see that the example 2, I solved for angle A by using inverses. So the inverse of tangent, once again, make sure your calculator's in degrees. I got 54.5 degrees. We're rounding it to the nearest tenth. And then the side length C, I used Pythagorean theorem because it is a right triangle, and got a hypotenuse of 8.60. Once again, the 0 there needs to be there because it's not 8.6 exactly. So we need to make sure we round that to the nearest hundredth and write 8.60. So that's a quick review of solving right triangles. That's not our main focus. Our main focus is to now solve triangles that are not right, once again called oblique. So let's take a look at that. So what is an oblique triangle? Just like I explained earlier, none of the angles are right angles. So we're going to be dealing with triangles that are no longer right triangles. Two types that we have, all acute angles for the first one. So that just means all the angles are less than 90 degrees. And then for the second one, you have two acute and one obtuse. So one of them, these two angles right here would be your acute angles that are less than 90, and then your obtuse angle is the one that is greater than 90 but less than 180. So make sure you're labeling your triangles when you go to do these. Like I said before, angle A matches up with side A across from it, angle B matches up with side B, angle C matches up with side C. So just make sure you guys are labeling your triangles so when you go to answer these questions, you'll be able to know where to place the values in the triangle. So what is the law of sines? Now the law of sines is this formula. I'm not going to do a proof of it. It is very extensive. It's maybe something we can talk about in class. But law of sines is A divided by sine of A is equal to side B divided by sine of angle B is equal to side C divided by sine of angle C. It may also be written the other way because these are just ratios. You can flip them around and it still works the same way. We have two cases that we're going to be dealing with law of sines. The first case is angle, side, angle. Once again, think back to geometry. That is two angles and an included side. So this represents two angles. But the important part here is that the side is included. It's in between those two angles. Whereas the second one, side angle, we have two angles and a non-included side. So once again, the side is not in between the two angles, it's non-included. So these are our main focus today, angle, and side angle. We will talk about in day 2, side angle. You might remember a little bit about this in geometry where it wasn't one of the ways that you could prove that two triangles were congruent. And so we'll talk about why that is and how that becomes important now when we get into solving for triangles. So that's more on the day 2 side of things. So now we're just going to look at a couple of examples here and be able to solve triangles that are now not right triangles. So example 3, you see that we're going to solve the triangle. Let's label everything. We'll call this side, or angle A, sorry. Angle B and angle C. Angle A is 50 degrees. Angle B is 30 degrees. And side A, which is once again across from angle A, is 2. So that means this side is C and this side is B. So we're missing angle C, and side B. Now, when you go back and look, on case 1, you have two angles on both situations, angle, and side angle. So no matter what, if I'm giving you two angles, you can always find the third angle. So that's kind of where we start with this, is that we're going to start with angle C, and we can find the measure of angle C by taking 180 and subtracting the two angles that you know, which in this case is 50 degrees and 30 degrees. So C is equal to 180 minus, in this case, 80, so it looks like 100 degrees. So C is equal to 100 degrees. That's the first part. Now we're going to use the law of sines to find side C and B, but we can only find one of them at a time. So use the information that you have for the angle and its opposite side. So we want to use angle A, 50 degrees, and the side opposite that, because when you use the law of sines, you need to have the angle and its side length as well. And then we'll use angle B and side B to find that piece of the information. So once again, going back to your law of sines, we're going to take the value of, in this case, A, which is 2, divide that by sine of the angle, which is 50 degrees. That should be equal to B, because we don't know B, but we know the angle, which is sine of 30 degrees. So there's your ratio. You're not going to write all three of them. You're only going to write two ratios at a time. And now you can cross multiply and solve for the ratios. So it'll be 2 sine of 30 degrees is equal to B sine of 50 degrees, and then divide by sine of 50 degrees. So 2 sine of 30 degrees divided by sine of 50 degrees is B is equal to 1.31. So we have angle C and we have side B. And now we have to find side C. So we're going to do something very similar. We're still going to use the 2 and the sine of 50 degrees. We're not going to use the B equals 1.31. The reason is because it's not an exact value. It's an approximation. So we don't want to use that. We want to stick with A that was given to us is now equal to side C over angle C, which is sine of, we found out, was 100 degrees. And that is accurate because we took 180 minus 50 minus 30. So we know that is correct. And then once again, we cross multiply and solve. And when we solve and cross multiply, divide by sine of 50, we get C is equal to 2.57. Side lengths round to the nearest hundredth, angles round to the nearest degree. So once again, we have solved the triangle. We found all the values that were missing for the triangle. You cannot use Pythagorean theorem. Remember, Pythagorean theorem only works for right triangles. So these triangles that we're dealing with are our oblique triangles. And one last thing, I forgot to label the triangle. It doesn't really matter in terms of our answers, but this was, in terms of our type of triangle, was side, angle, angle. So the side was not included. That matches back with what we did here, side, angle, angle. All right, example 4, solve the triangle. Once again, setting it up in terms of angle A, B, and C. So we know angle A is 35 degrees, angle B is 15 degrees, and side C is 5. So this is an example of angle, side, angle. So it's the other example that we had on our case 1. So these are the two possibilities that you can have. We don't have side A, and we don't have side B. Go ahead and pause the video and see if you can just work through this example. It's very similar to what we've already done. You can find the third angle and then use your law of sines to figure out the rest. So I worked through and I found angle C by taking 180 minus 15 minus 35, which is 130 degrees. So I found the angle. Then I had to use that angle because the side across from that I knew was 5. And then I used A, and the sine, or the angle across from that was sine of 35. So cross multiplied, divided by sine of 130, and got A is equal to 3.74. And we can do exactly the same thing to find side B, as we'll take 5 divided by sine of 130 degrees is equal to B, and now B is over sine of 15 degrees. So then I cross multiplied and solved the rest of it, divided by sine of 130 degrees, so B was equal to approximately 1.69. We found the remaining sides. Kind of a quick check on this, if you're once again kind of going back to geometry. Remember, your largest angle should have your largest side length. And so as you look at each of these, your smallest angle should have your smallest side length, which it does. And then lastly, your kind of middle angle, 35 degrees, should have your middle value in terms of your length. So just kind of a quick check, make sure you're doing it correctly as you're solving using laws. So one of the application problems that we're going to be working on is talking about bearings, and so it gives you a direction of things. And so just to kind of, before we get to the application, what does this mean? When it says south 40 degrees east, you have your south, so south going that way, so south, and then 40 degrees east, so you have east on the right hand side. So from that you create a 40-degree angle from the south. So that's what that bearings in terms represents. So look at the next one, north. So now we're going north, and it's 38 degrees east. So now, because we're going north compared to south, now we will be going this way, which represents the 38 degrees there. And then once again another south, so if we go south and then 40 degrees west, it's 40 degrees this way going to the left. That represents the 40 degrees. So we'll look at a couple of these questions and see if that kind of makes sense when we go to set it up and apply it. So let's take a look at example 5. A boat is sailing due east parallel to the shoreline. So I also have a triangle on the right side of the picture here, so we can kind of do both parts as we go along. At a given time, the bearing to the lighthouse is south 70 degrees east. So right here at this point, you have south 70 degrees east. So right there, that angle is 70 degrees. So as part of my triangle, it's right here. So it's out on the outside there. So that's 70 degrees for that angle. And 2.5 miles later, so as the boat is traveling, 2.5 miles later, the bearing is south 63 degrees east. So on my triangle to the right, that's 2.5, and then south again, 63 degrees east. So on this triangle, it's this part, 63 degrees. But we have 63 degrees plus that 90-degree angle there. So if you add those up, 90 plus 63 is 153. So this angle is 153 degrees. The lighthouse is located at the shoreline. Find the distance from the boat to the shoreline. So we want to find the distance, which is from the boat to the shoreline. So that's D. So this distance here is what we want to find. Okay? So given that information, what else do we know? Well, if this is 70 and this forms a right angle, then this must be 20 degrees. If this triangle here that we have 20, 173, so we know that this angle down here must be 7 because 20 plus 7 plus 153 is 180 degrees. So we know that. Let's label our triangle here. We'll call this A, B, and C. So we have the side opposite C. We don't have B, and we don't have side A. Now we're looking for D. So D is not even a part of that triangle, but it is a right triangle down here. So if we can find side B, that will then help us use right triangle trig to find side D. So given the information here, can we use law of sines to find B? So we're looking right now to find B. So let's see. We can do angle C and side C. So we will do 2.5 over sine of 7 degrees is equal to side B over sine of 153 degrees. And when we go and multiply and do our cross multiplying, and then we end up dividing by sine of 7 degrees, we get a B value that is approximately 9.31. Now, I'm not going to approximate that and use that later on. I want to use the exact value. So we're going to hold that into our calculator, and we're going to use that again. So the next part, now that we know that B is approximately 9.31, we're now going to look for side D using right triangle trig. So find D. Well, now we know that this angle is 70, and we have the adjacent side and the hypotenuse, then we can use cosine. So we'll do cosine of 70 degrees is equal to the adjacent side over the hypotenuse, and once again, this 9.31, we're not going to use exactly, we're going to use, or not approximately, we're going to use the exact value in the calculator. So D will be equal to that value times cosine of 70 degrees. And once again, this value, we're still going to use the exact value from the calculator. So this is going to be the value that we use from the calculator. And so if you press cosine of 70 times, the 9.31, you can press answer on your calculator and it'll do the 9.31 times 70. And if you do that, and we're going to round this to the nearest hundredth, you should get that the distance is approximately 3.19, and then that's going to represent the miles that the boat is to the shoreline. So the distance the boat is to the shoreline is 3.19 miles. So take a minute now to kind of write the summary of what the notes were today, what those important pieces are as we go and start looking at the homework. So here's what I came up with in terms of my summary if I'm looking back at this and trying to pull kind of everything out. Obviously we did law of sines. There's your formula that we have used when you have angle, side angle, and side angle, angle. Also remember angles are rounded to the nearest tenth and sides are rounded to the nearest hundredth. And then on the other side here I put Pythagorean theorem and SOHCAHTOA, or our trig ratios that we had learned, only work for right triangles. So that's not something we are necessarily getting rid of, but we can only make sure we're using that when we're dealing with right triangles like we did on that last example there.